So the first speaker of our session is Jiakang Bao from University of Tokyo. And so he's going to tell us about artificial intelligence and whether it can prove toric Calabi-Yau. So please go ahead.
Okay, thank you. Thanks for the invitation. And yeah, I'm sorry, unfortunately, I cannot be there in person. Right, so this is the title of my talk, but if you check the abstract, you'll see that I will mainly focus on the gauge theory and the algebras regarding the toric Calabi-Yaus. And towards the end of my talk, I'll mention some machine learning application regarding some like thermodynamic limits in this toric Calabi-Yau setting. So, right, so here's the plan of my talk. So first I'll mention some background very quickly, including the Brent-Hartlings, quivers, and the crystal melting model. And then I'll talk about some BPS algebras in this quiver setting, which are known as the quiver Yangians. So I think Wei has give a talk like in the first week, like in October, and she gave a very nice talk on this quiver Yangians and its like various connections to different areas. But for completeness, I also mention the definition, and then I'll mention the R matrix formalism in this context, and then I'll talk about the isomorphism of these algebras and the Seiberg duality, and finally in this section I'll mention some non-toric examples which are associated to some affine Dynkin types. Then I'll switch gear and talk about the so-called thermodynamic limits of the crystal. So, well, first I'll mention something like exotic from number theory, which is called the Mahler measure, and also talk about the amoeba, and then I'll discuss the machine learning, the genus of the amoeba. So this is our setting. So we have some toric Calabi-Yau threefolds with these D branes wrapping the compact cycles, and they'll form the BPS bound states, which are mathematically known as the generalized Donaldson-Thomas invariants. And from the geometry, we can construct the quivers, giving us the gauge theory using these inverse and forward algorithms, which are studied in many papers. Well, here I'm just giving listing some of the authors. It's never a complete list, but it's a well-established story. And so, for example, this is like the simplest toric diagram, and this is we can construct a bipartite graph, which is called the diamond model or Brent-Hartling. And I'm not gonna discuss how to start from this toric diagram and go to this bipartite graph, but we'll always assume that we know there is such Brent-Hartling or dimer for any toric diagram. And this bipartite graph is embedded on the torus. So this line is identified with this edge, and this edge is identified with this edge. So essentially, in this example, there is only one face, which is this one, and we construct a dual graph, which is essentially the quiver of the gauge theory. So there is a single node because we only have one face here, and we have three edges. One is this one is this one, and the other is this one. So we have three arrows in the quiver. And since it's on the torus, so it's periodic. So we can just draw it like a tiling. So I'm omitting the white and black nodes. And then from this periodic bipartite graph, we can construct, well, of course, we have the dual graph, which is the periodic quiver. And the melting crystal model tells us that these like molten crystal configurations, they are in one-to-one correspondence with the BPS states. So let's start with the perfect matching, which is a collection of edges such that each vertex in this bipartite graph is incident to exactly one edge. So here, this is an example of a perfect matching where these blue lines are the edges I choose in this reference perfect matching. And for like future convenience to help us visualize this sort of crystal picture from perfect matching, I draw these red lines that goes through these edges that are not chosen in this reference perfect matching. Then I would like to change my perfect matching. So for example, I can remove the maybe I shouldn't erase it. Then I can remove these 3 blue lines in my perfect matching, but then I have these vertices left, so I need to choose these the 3 orange edges to connect to these 6 nodes. So now my new perfect matching looks like this. So it's well essentially this one here, which are these the 3 orange lines here, and the remaining are the blue ones. So this is my new perfect matching. But from this new perfect matching, if I still draw these red lines that goes through these edges that are not chosen in this perfect matching, I can actually really see like some box here, which is in bold. Okay, maybe I should change the color. I can really see something like this, which looks like a box. So in this brain tiling picture, and of course I can change another perfect matching, which removes like these edges, but then instead I choose these orange ones, and then again draw these red lines. I can actually see a 2-box configuration. And I mean, we can just keep going. Like this is a visualization for the 3-box configuration. But of course, this is not a. I mean, this is just like for us to really like see the picture, like these boxes from the brain tiling. Most of the time, we can work with the periodic quiver, which is a dual graph. So this crystal is actually because this periodic quiver is also on the plane, so the crystal is actually a 3D uplift along the 3rd direction. So this is so for example, if I start from this node in the quiver, then I have 3 arrows going to these 3 nodes, and this is like in my crystal I have this initial atom, and then I go to these 3 atoms, and this is another to view this crystal from a different angle. So we can actually, so these 3 ridges are the like 3 axes here. So we can actually see that in this case it is the plane partition, which is like the 3-dimensional Young diagram. So but this is 2D. We want to get a 3D crystal. So the rule is to, given the path in this periodic quiver, we can always write it in this form, which is V times some loop to the power n. So this V is the shortest path from your initial node here in the quiver to some node in this quiver, and then omega is the loop, close the loop in your path, and you go around this loop n times, so it's like to the power n, and then for this path, we place this node or this atom just going along this surface, along this path, shortest path V, and then we go down depth n, and this is where we put this atom following this path. So for example, well, this is our previous example, and we have like 3 arrows in the quiver with this superpotential. So for example, if this is still my starting atom or starting initial node, and I want to go to this node, but I'm not following the shortest path. Instead, I'm going through this path. But using the F term relation, I know, well, this is the path because this is Z, y, y, x according to this label. But then I can, using the f-term relation and exchange y and z, it will give me actually this one, y, z, y, x. So this is like the green one is like the shortest path. Then this is like going the loop once. So I know this is in the crystal, this is this node on the surface, which is followed from this shortest path. And then because there's one loop, so I put it at depth 1. And likewise, I can go through this like longer path, and it turns out it's essentially the same shortest path, but with the loop going twice. So I put this atom at depth 2. Right, basically this is the construction of a three-dimensional crystal. But of course, as a like crystal melting, it has to satisfy some melting rule. So for example, we know for the three-dimensional Young diagram or plane partition, we only have like 3 possible configurations with 2 boxes or 2 atoms. Of course, first there is nothing, so it's just empty. And then we have 1 atom, which is like level 1. And then we can have 3 different configurations at level 2, which corresponds to these 3 arrows in the quiver. And of course, at level 3, we can have different like configurations, like something like this, or something like this. I mean, if we just, but this one is not allowed because of this melting rule, which tells us that a box is okay. This lambda is the crystal, and this tells me that an atom or box is in the crystal whenever there is an edge such that x dot box, this new atom, is also in the crystal. In other words, x dot this box is not in the crystal whenever there is this box is on the crystal. So for example here, as I was saying, this is not allowed because if we consider this green atom, this green node here, which corresponds to this green node here, this is actually well, something like this. It's equal to this red x, which is this red arrow, dot this orange box, which is this one here. But this orange one is not in my crystal. And following this rule here, I know that this one should not be in my crystal. So this is not an allowed configuration. So using this, we can find all the possible configurations. For example, these are like different like crystals for different cases. Like this is the conifold, and these two are the like C times C2 over Z2 geometry. So with these different shapes correspond to like different cyclic chambers. So this is the background. And now I want to talk about this quiver BPS algebra, which is realized by this quiver Yangian. And well, in short, this is because they have the crystals, these crystals we were discussing as their representations. So if you attended Wade's talk in October, you've already seen these relations. So the algebra is essentially, they are generated by these 3 types of modes, which we call psi, E, and F, with N being, well, with N here. And this superscript A labels the quiver nodes. And they satisfy, well, we can write this compactly in terms of these 3 types of currents, and they satisfy these relations. So there is a key factor or key function in these relations, which is called the bound factor here. So essentially in the denominator, so if I denote this as phi AB, then the denominator has this Z plus HI, where HI is the weight associated to each arrow, and this I in the numerator, they correspond to all the edges from A to B. And in the denominator, we have Z minus HI, where these I's are now given by the arrows from B to A. So this is the bound factor. And there is a Z2 grading, or if you like, the both Fermi statistics for this algebra, which is determined by the number of self loops in the quiver for each node. So, for example, in our previous example, this one, we have 3 self loops, and tells me that if there is an odd number of self loops, then this node, we say it's bosonic, and otherwise it's fermionic. And then the EF generators, they would have the same Z2 grading as the node, and the psi is always bosonic. So except this case we were considering, for all the toric examples we'll consider, there are only 2 cases. Either it has just 1 self loop, which means it's bosonic, or there's nothing, no self loop, then it is fermionic. So these are the only 2 cases we'll see for the toric examples. And in this bound factor, we mentioned that there are these weights assigned to each edge. They are not completely independent, so they have to satisfy these 2 sets of constraints. One is called the loop constraints, and the other is known as the vertex constraints. So for any monomial in your superpotential, there will have a set of edges, and the weights of them should be summed to 0. So for example, if I have this x1, x2, x3, x4 in the superpotential, then I would have this constraint. And for vertex constraint, it's just like the sum of the edges, of the weights of the edges is 0 again, but with the sign. So for example, if I have this configuration in the quiver with these 2 coming in and these 2 going away, so if I choose this coming in as plus sign, then I'll have this hx1 plus hx2 minus the other 2 to be 0. So this gives me the vertex constraint. And for Calabi-Yau threefolds, due to these 2 types of constraints, I would eventually have 2 independent parameters. So we'll just call it h1, h2. And of course, it's convenient to also introduce h3, which is such that does h1 plus h2 plus h3 is 0. So these 2 correspond to my isometries for the Calabi-Yau. And of course, for the algebra, there were some sort of like a hierarchy. So we can have trigonometric versions or elliptic versions for the algebras, which essentially just so here this is the bound factor. If you like, we can write it as zeta plus z plus hi for the numerator, and likewise zeta minus hi for the denominator. Then here in this example, zeta of z is just z, but then I can change this to like trigonometric functions or like some Jacobi theta functions, which gives me the other versions. But I'm not going to talk about these in talks today, so I'll just focus on this rational case. Okay, in terms of modes, we can rewrite the relations like this, which looks more complicated with the notations like introduced here. Yeah, of course, we don't have to remember these relations. I just want to show that there is this relation. But, and of course, it turns out that if we want to really get the correct BPS spectrum, so when we act these generators on the crystal, as we were saying, the crystal, there are these crystal states, they form the representation of the algebra. If we want to get the correct number, like for example, for the plane partition, we know there is like an empty configuration, and there is one configuration at level 1 and 3 configurations like these, like these at level 2, etc., etc. It turns out we also need some extra relations, and these are called the third relations. For some examples, for some cases, we know the third relations, but in general, it's still not clear like what the exact third relations are. So in our following discussions, I'll just always assume that everything would still work in when we include these third relations. Yeah, so this is the crystal representation. So this is this lambda is a state which is labeled by one crystal configuration. Then the first one just tells me that it's an eigenstate of the psi current, where this capital psi function is given by a product of the bound factor, and E, we can see it's just adding atoms to the crystal, so it's like sort of like the raising operator with some coefficients here. And F, it removes atoms from your molten crystal, so it's like the lowering operator. And these residues, because the pose in this function actually tells us which place we can add, like gives us the coordinates of the atoms where we can add or remove these atoms in the crystals. So I will mainly focus on the very special class, which are non-chiral quivers, so they are just symmetric quivers. Namely, so if I have two nodes and I have an arrows going from this way, then I should also have an arrow going from that the opposite way. So these are symmetric. For toric cases, these are the toric diagrams without any internal points. So we only have two classes. One is called the generalized conifold, which is given by this trapezium, and then there is something called this, which is this toric diagram. So essentially, this is the quiver associated to the generalized conifolds. But here, I'm not giving you like the full information, because this is just the shape of the quiver. But at each node, I could have one self loop or have nothing. I mean, no self loop. And then for these edges, there is always one pair of opposite arrows. So essentially, it looks like this. And maybe sometimes maybe somewhere I have some self loops, but these are the quivers for the generalized conifolds, and the number of nodes is determined by these M and N. So, well, actually, we can see like this is the shape of the quiver, but we know by looking at this diagram, we know it's just the Dinking diagram of this untwisted affine algebra. So, and indeed, there is a connection to these affine algebras. And these are the weighted assignments to the edges. So if I have, so for example, if I look at this node, which has a self loop, then the edges connected to it would have plus minus H1, H2, and these plus minus are just my choice. So once I fixed one plus minus sign, then the others will be fixed. And or I can have a node without any self loops. Then this is the like weight assignment to the arrows. And of course, you can have different faces. Namely, you can have different quivers for a given generalized conifold, and these are related by Seibach duality. And the other one is similar. So this is the quiver diagram, and we can see if we just look at the shape of this diagram. This is actually the Dinking diagram of this affine superalgebra, and also shown as shown in this paper when they first introduced this quiver Yangian. For these symmetric quivers, this psi can be expanded as this. So you don't have, basically you don't have negative modes except this one, which can be treated as psi minus 1. So now I'm going to talk about the construction of the R matrix, and I'm not going to go through all the technical details, but I just want to show you the general idea of this. So for convenience, it will be convenient just to introduce some new current, which looks very similar to the psi currents, and of course here we're always focusing on the non-chiral quivers, and they will satisfy these relations or in terms of currents. And it turns out my action of psi on the crystal looks like this. So here, because I also call this H, so I changed the weights to be to epsilon, but I mean this was the H, namely these are the weights assigned in my quiver or in my crystal. And it turns out for generalized conifolds, the psi, indeed this psi current, well, can be expressed as in terms of H. Yeah. So anyway, I guess I don't have to really introduce these concepts like the R matrix and the transfer matrix here, but well, essentially, we're just gonna build or construct the R matrix, the actions on the crystal on my states of the in my Fock spaces using the RTT relation, and these states in the Fock spaces are labeled by the 2D crystals. And in my notation, I use this T sub mu1 mu2 as a matrix element of T sandwiched by the two states mu1 mu2. And it turns out that we can write these currents, or the first several levels of this matrix, these matrix elements in terms of the currents like this. Well, it's kind of sort of intuitive because H is having these crystal states as their eigenstates, so it's kind of so it has nothing. Basically, it's the empty T empty, and then E creates a box. So I have a box here, and F annihilates a box, which intuitively looks like having a box on the bra vector instead of the cat. So it looks like this, and psi is slightly more complicated. But with this normalization, we can consider the R matrix, its action on this chain of crystals, 2D crystals. And indeed, if we apply the RTT relations on the empty vectors, it turns out that this recovers my relations for the H currents, which simply tells me that they commute. And of course, I can go to the next level and using the RTT relation, and then I will get some action that looks like this. And with some assumptions, we can and using the fact that all the higher levels, of the generators in my algebra can be obtained from the lower levels, we can obtain the action of the R matrix on the crystals with more atoms. And then using this story, we can obtain the Bethe ansatz equations following the story by Nekrasov and Shatashvili. Basically tells us that we have this superpotential for my supersymmetric gauge theory, and the vacuum equation is exactly some Bethe ansatz equations. So here it's, well, the full expression is a bit complicated, so I'm not gonna write it down, but this the pictorially it looks like this. So I just consider the eigen value equation for some operator T and acts on this vector B, which we may call the Bethe vector, where this B looks like this, which is essentially, a net looks like this. and with this chi defined like this, and this t is something here. So essentially what we do is just to use the RTT relation to push this line go all the way above. Then I'll get this configuration, and then I can project this to some broad vectors, and then I'll get the set of Bethe equations. I believe you've seen this if you attended Wade's talk, which is the Bethe ansatz equation, which is given by the bound factors. And so we're just focusing on the non-chiral quivers, or these quivers associated to those toric Calabi-Yaus without like compact divisors. But there are, for chiral quivers, like these larger toric diagrams. When you have internal points, it turns out there are some obstructions to construct these to obtain these Bethe ansatz equations, to construct some integrable systems given in this paper. So now I want to talk about the algebra, this algebra and the cyclic duality. So in short, cyclic duality is just so in the quiver we pick a node to dualize, and then we just reverse all the arrows, the directions of the arrows connect to this quiver. So here it's going this way, and then we're just going this way. Then for each pair of arrows that are reversed, I just add a new arrow, which we may call it meson, connecting these two nodes. And of course, you can change the superpotential and also the Brintalines accordingly. But that's enough for our purpose here. So the conjectures, of course, your quiver BPS algebras, they are isomorphic for cyclic geoquivers. And in fact, we can prove this for the generalized conifolds. I mean, there is another one which, if you remember, there is another non-chiral quiver whose toric diagram looks like this, and the quiver looks like this. Well, there is only one toric face here, so we don't really have to worry about it. But there is another face which is not toric, and in fact, we can show that if we construct, we similarly define the quiver Yangian for the non-toric face, they are also isomorphic. But I will mention this later. So the idea is actually using something called odd reflection for the underlying affine algebra. Because remember, we have like the shape looks like this, which I mentioned that it looks like it is actually the affine thinking diagram. So we just using the odd reflections that takes us to the different thinking diagrams for the same affine algebra, affine superalgebra, and we generalize this to the quiver Yangian case. And this essentially is the cyclic duality, how cyclic duality acts on the quivers. So to do this, because we have like infinitely many generators given by like En, Fn, and psi n. So just to make our life easier, we want to reduce to a finite number of the generators, so that we can actually obtain like the isomorphic map more easily. So first, we notice that actually if we play with these relations, it turns out that those modes at higher levels, like at level m+1, can be obtained from these modes at lower levels, which is the level at m. And for psi m+1, it's just the commutation relation. So once we have these two, we can obtain the psi. So here, this psi 1 tilde is essentially psi 1, but with some extra pieces from psi naught. This means the algebra is finitely generated by these four sets of generators. But of course, the relations, we still have this set of relations, and in fact, they are finitely presented as well in namely that these relations we have, which involve all these infinitely many generators, although they can be eventually expressed as these four generators, but still we can still have like infinitely many relations. But here, finally presented tells us that we can also just consider finitely many relations, because all the relations involving the higher modes, they can be derived from these relations from the low with the lower modes, which are given by actually six sets of the generators, which are like at level 0 and 1. So to prove the isomorphism, it just suffices to consider these generators. So let me first show you the one at level 0. So this is the transformation. So besides note is the one our starting quiver, the modes associated to the starting quiver, and the primed ones, they are the one after, they are the one after subduality. And here we're always dualizing the fermionic nodes, which does not have any adjoints. So here this digamma, because it looks like F, so I choose this symbol. But yeah, anyway, this is the node we dualize, and for its neighbors, because we always have this necklace quiver, so the only two nodes connect to the dualized one, they transform like this, and then the other nodes, the generators are unaffected. So I'm showing you this because this is precisely the odd reflection of the of this affine Lie superalgebra, because they are these zero modes, they actually give us they are the Chevalier generators for this affine Lie superalgebra. And yeah, these are just how odd reflection changes the roots for the affine Lie algebras. And it's more intuitive to see this from the thinking diagram. So in my thinking diagram, there are two types of nodes. One is bosonic, one is fermionic. So always the odd reflection always acts on the fermionic ones, and it will change the parity of its neighbors. So if I consider this node, where gray this color gray, the gray color indicates the fermionic ones, and the white color indicates the bosonic ones. And if I choose this node to act my odd reflection, then I will just change the parity of its neighbors. So I will get this white will be changing to gray, and this gray will be changing to white. So in my quiver, so which corresponds to this, because it's fermionic. So, and indeed in the quiver it's still fermionic, so I don't have any self loops. And then for the bosonic one, I would have a loop here. And if I dualize this node, it will just give me this one, the dualized one is still fermionic, but then it will change the parity of its the two neighbors connected to it. So I would have some configuration that looks like this. So usually we can it will be just convenient, for example, say to start from the so-called distinguished phase. So whose thinking diagram we only have, okay, it's black. So we only have two of them to be fermionic, and then I can start to apply my odd reflection, so it will change. So for example, if I choose this node, then odd reflection will change the parity of these two nodes and will paint them black or gray to make them fermionic. And likewise, I can always start from this quiver. And then if I again dualize this node, then it will change the parity of its neighbors, so they will make these two fermionic. And if I repeat this, and eventually I'll get all the faces of of the same toric geometry. So now the job is just to, well, as we were saying, we only need to consider the generators at level 0 and level 1, and for level 0, it's essentially odd reflection. So we just need to generalize this to level 1, and here is the isomorphism. But actually, when we were trying to obtain this map, we didn't directly work on these modes or this presentation. We consider something which is analogous to sort of like the classical or finite Yangians, called the J presentation, which is defined like this. So essentially, it's still the level 1 generators, but we have some extra pieces look like this. It's well these are like the basis of your root space of the underlying finite algebras. But using this, it's actually much easier to obtain the transformation or the isomorphic map. So this is the map for the J presentation, the level 1 essentially generators. So as we can see, actually they look really similar to the ones for level 0, because here I have minus psi, and here it's just minus j of psi, and I have here I have EE commutator, and here I have E and just JE commutator. The only difference is this part, where here it's psi not A, psi not F, and here it's J plus J, but with some extra corrections. But once you check, you can obtain this extra corrections or these relations, these maps for using some of the relations, and then you can verify this with the other relations, and it turns out this is indeed an isomorphism. Of course, again, this is only for non-chiral quivers. For chiral quivers, it's much more difficult. Yeah, you might, I mean, well, one possible way is to consider maybe, because these topic dualities are essentially quiver mutations, so maybe one can use something from cluster algebra, etc., to get this, but to get some sort of isomorphic map, it turns out it doesn't quite work. So it's still an open problem to show that the quiver Yangians are indeed isomorphic under subject duality for general cases. Okay, in view of time, maybe I'll skip this part where basically it's some bit. Oh, sorry. Yeah. Okay. Sorry. Yeah. So the other fun thinking types, which are associated to the other, because before we were just talking about these A types, and of course we can consider other fun thinking cases, but of course we are not sure whether they are really the BPS algebras because they're not toric. But anyway, we can also consider the super cases, and then we have a different type of node which has 2 loops. And for those involving these 2 loops, the algebras may not be isomorphic. Well, actually, I mean, they are not really isomorphic. Okay. Yeah. So since I'm about to talk about the thermodynamic limits, maybe I should first mention some other possible directions. So for example, I didn't mention this connection to the W algebras or vertex algebras, but you can for generalized conifolds, like for these non-chiral quivers, we know there is a surjection from the quiver Yangian to some rectangular W algebras, but in general, we don't even have this construction basically for the vertex algebras. And of course, we can consider the other cases, like the trigonometric versions, elliptic versions of the algebras. And basically, we just replace so for this BAE story. So basically, we just replace the bound factor with the corresponding functions. If you remember this zeta, then we just replace this zeta with the corresponding functions, and then we can obtain the Bethe ansatz equations. And turns out the elliptic case also appeared. This the so-called BAE also appeared in these papers regarding the superconformal indices and black hole microstate counting. And also we can have dynamical R matrix, and it's really worth mentioning that there is such Bethe gauge correspondence appeared in a very recent paper here, where the authors used this elliptic stable envelopes to for the Higgs branches of these 3D unequal 2 quiver gauge theories to obtain this Bethe ansatz for some superspin chains. And of course, Shailesh also gave a talk this week mentioning discussing their very nice papers on machine learning R matrix. So here we have some R matrix, but of course it's slightly different because, well, first of all, the representation here given by the crystal is infinitely dimensional. So, but maybe we can also try to see if we can apply machine learning to these R matrices. And then I'll talk about the thermodynamic limit for the crystal melting. Well, first, let me just introduce something called the Mahler measure, which comes from number theory. So for some Laurent polynomial, I can always define something looks like this, which is log of this Laurent polynomial, and then integrate over the torus. And I can generalize this with introducing these extra x, and these are called the ranking functions. So here we have considering the toric polygon, so it's always C2. So we only have 2 variables. So for example, this is a Newton polygon, the toric diagram, and I know this one is 0, 0, so it's a constant term. This is 1, 0, so it's Z1, W0, giving me this term, etc., etc. And then we can follow in this formula to compute the Mahler measure. But in general, we would just compute. So here we'll always fix the constant term. We'll always choose the constant to be some variable k, and then we just expand it in terms of k, which looks like this. And the ranking function is much harder to compute, but the shape we know looks like this for the F0 case. So we can project the shape of this ranking function to 2D, and then we'll get something called the amoeba, which first appeared in the context of string theory in this paper, talking about the mirror picture. And this amoeba is given by the set of points of, well, satisfying essentially the zero locus of the Newton polynomial. And we're calling this the thermodynamic limit, because this amoeba or this ranking function is the limit shape of the crystal. So this is like the C3 case, and we start to melt this corner, and in the thermodynamic limit we'll get something like this. And for the F0, so this is like the shape of the ranking function, and this is the amoeba, which is the limit shape of the crystal. Yeah, and so recall we have this diamond model of brain-tiling, and for each edge we can assign some weights look like this, and we can also then define this weights for the perfect matching as well. So this is x, the weight is like x to some minus curly e, and this curly e is what they call energy. So the energy of the perfect matching is just the sum of the energies of its edges. And then we can define the partition function for a finite graph. It just looks like this, which is the sum of all the weights associated to the perfect all the perfect matchings. And the diamond model is like infinitely large, so we just define the partition function as this limit. And then, as shown in this paper, that this partition function is exactly given by the Mahler measure. And of course, for the ranking function, there are also some thermodynamic limits giving us the BPS partition function discussed in this paper. And then there is a special family of dimer, which is called the radial dimer, where each face is inscribed in the circle of the same radius. So we can show that the maximization of the model measure is the same as a maximization, because we can assign these weights using there was some canonical choice to assign these weights, which is related to the R charges, and then we can actually show that these two are the same. And we tried some examples, and we conjecture that this is also true for non-isolated cases. And yeah, I only have like 10 minutes, so maybe I will just briefly mention that there is also another duality for these gauge theories, for these quiver gauge theories, which are called the specular dualities, that they preserve like the larger moduli space, which is called the master space. And the model measure also has some nice properties under this specular duality. So now I want to in the last like 8 minutes, I want to mention some machine learning about the genus of the amoeba. Well, since this workshop is also have machine learning as a theme. So and I should also mention that recently, so here I'm going to just talk about the 2D amoebas we've seen. But recently in this paper, they have this 3D amoeba as well. And in this paper, there is also machine learning regarding the co-amoeba, or what we call the alga. So actually, we're not really machine learning, like getting some sort of expressions or recover some expressions for the genus for the actual amoeba, but we're actually considering the lopsided amoeba, which is defined by this which says this P here is not lopsided. Somehow it's called lopsided amoeba. So for Newton polynomial or Laurent polynomial, I have these monomials, which I call them M1 up to MK, and I define this F curly bracket XY as a set of the absolute values of these monomials. And we say this thing is lopsided if there is one element which is larger than the sum of the remaining. So it's lopsided. And then we can use this to define the lopsided amoeba. And it turns out, okay, this is a typo actually. It turns out the amoeba is always contained in the lopsided amoeba. And we can actually consider like sort of more complicated Laurent polynomials, or like lopsided amoeba given by, so this P is just my Newton polynomial for my toric diagram. And then I consider this the product of a bunch of these Newton polynomials with the variable given by these. And then it turns out that if I consider the amoeba associated to this Newton polynomial, as n goes to infinity, these lopsided amoeba would approach or would give me the actual amoeba. So I shouldn't have this n here. So here let's just focus on this lopsided amoeba. So for example, let's consider this F0 case, and then we just vary the coefficients here. So our coefficients, this 5-dimensional vector will be our input, and we just the output will just be the genus. So it's either 0, which has no holes, or either 1. So for this case, because it only has one internal point in the toric diagram, so it only has one hole. And actually, we already know that for this lopsided amoeba, this is the condition to determine the genus. So essentially, it's given by these inequalities. But if we use principal component analysis, it turns out that we can project these data points into which gives me something like this. The picture looks like this. So, and it turns out like we can fit the x and y coordinates. Well, just here like these coordinates, and it will give us something like this. So basically the idea is that we first of all, I mean, of course, we know this is the condition. So let's first try plot x against C5, and turns out it's something like this, which is like almost perfectly x equal to C5 up to some errors. And of course for y, which involves C1, 2, 3, 4, it's more complicated. But if we fit this y with the absolute values of these c's, it turns out there's some approximation looks like this. And this is actually almost like this approximation for the square roots, which looks like this. So if we plot against these two, this two absolute value of y against this a minus 2 delta, where a is defined like this, and delta is the one we fit minus the actual y, and turns out it's also a line like this. So in this sense, given that of course, given that we can derive this expression, we can sort of recover these expressions from this PCA analysis. Yeah, I guess that's all I want to talk about. Thank you.